All right, this is going to be part 4 of the study guide. So let's go and get to it. All right, question number 1, what is the degree of the vertex H? I'm just going to go ahead and do everything. It just makes life a lot easier here. All right, so degree of vertex H is being connected 1, 2, 3, 4, 5 times. M is being connected 3 times. A is being connected 1, 2, 3, 4, 5 times. And then T is being connected 3 times. All together, I know the question's not asking, but the answer would be 16. All right.
Excuse me. That's not the right answer, though.
All right, question number 2, basically the same exact thing. So A has a degree of 3, B has a degree of 5, D has a degree of 4, C has a degree of 2. You do the math, add everything up, and it looks to be about 14. There's your degree. All right, so find the minimum project time. We've done this several times. Anything connected to start will have a start time of 0. And then, let's see, D would start at 4. Vertex E is a merge. You always want to take the largest total, which in this case would be 5. And then, let's see, F, G, and H will be 6, 6, 6. J will be 6. Or I would be 6. J would be, again, it's another merge. You take the largest total. 6 and 2, that's 8, or 6 and 3, that's 9. We always take the largest, which is 9. Same thing for K, which would be 9. That would be 15. That would be 20. So minimum project time is 20. All right, very similar. Find the critical path. First thing we need to do is find the minimal project time. So A, B, C would be 0. D would be 5. E is a merge. That'll be 7. F is 10. And then G would be 15. That'd be 15, which would be 26. Now, doing the critical path, the way I taught it was going from left to right, but I like to go right to left because it just makes life a little easier. So very simply, I'm at 26. So I'm at 26, I got to get back to start. All right. So all I'm going to do is I'm just going to add what two numbers gave me 26. So 15 and 11 gave me 26. Now I'm at 15. What two numbers gave me 15? That would be 7 and 8. What gave me 7? That'd be this, and then back to 0. So it would be start, B, E, G, finish.
So you're starting, you're making.
All right, for this question here, it says EST for R. So basically what that means is what number would I put on top of R? So again, all we're going to do the same exact thing we just did for the last two. Does the merge, that'll be 10 or 7, 10. That'll be at 12. That would be 12 as well. Let's see, that would be at 12 as well, I believe. I'm going fast. I think we're good. All right, Q would be a 16, and then S would be 16 as well. That would become 18. I know I'm not asking the solving for it, but anyway, that would be 16. All right, next question. We got a draw. Here's what we're using: A, B, C, D, E, and F. Try to make it more in a circular pattern. There's no F. All right, there we go. All right, so A, B, B, A, B, C, C, B, another C, B, another A, or an AD. Let's see, EB is right there. CA. Okay, we got to loop that one. I did not put that one right. All right, DC, CD, EA, and lastly, double A. All right, so from here, find the total degrees of the graph. Very similar to like the first couple questions. A has a degree of 1, 2, 3, 4, 5, 6, 7. B has a degree of 5, 6. C has a degree of 1, 1, 2, 3, 4, 5, 6. D has a degree of 3. E has a degree of 2. Add everything up. It looks to be 25. There we go. So,
I should.
I'm sure you should. All right, so question number 7. What we're dealing with is an Euler circuit. Now, if you remember the Euler circuit, all of the degrees must be even. All right. So first thing we got to go through all the degrees. That is a 2. That is a 4. That is a 2. That has a 4, that has a 2, and lastly, this is a 4. So obviously, yes, it has an Euler circuit, but remember, you have to use all the vertices. All right, all the vertices, all the edges. Basically, you're retracing the graph. All right, you can start anywhere with an Euler circuit. I'm just going to start at this guy right here. Just watch my pen. Here we go. Started and ended at that vertex. All right, so next one we're dealing with a directed Euler circuit. Again, Euler circuit, but here's the problem. And since we're dealing with arrows, what you need to make sure is that everything that's going in equals what's going out. So like, for example, look at vertex E. Vertex E has one arrow going in, one arrow going out. We like that. But if you look at like vertex D, and there's several violations here, vertex D has two arrows going in, one arrow going out. So because of that just one vertex, and there's several in this example, this is going to be a big fat no. It does not have a Euler circuit. All right, next question here. Does the following graph contain an Euler path? Now, with an Euler path, the degree rule is that you have to have exactly two odd vertices. All right, everything has got to be even, but you got to have exactly two odd vertices. So first off, let's go and get all of our degrees. Vertex A has degree of 3. That's our first odd. B has 2. C has 3. That's our second odd. As long as we don't have any more odds, then we are good to go with this being an Euler path. This has a degree of 2. This has a degree of 4. This has a degree of 2. All right. So we know yes. The answer is yes, it has an Euler path. Now, where you start, you have to start at an odd vertex. Okay, you have two choices, so I'll give you a hint. Because it's a path, you're going to start and you're going to end at different spots. Okay, if I start at one odd, I'm going to end with the other odd. So I'm going to start with A because I wanted to, and I'm just going to start tracing. So here we go. Yes, you can go back to the same vertex more than once. So there you go. I started with A, ended with C. With a directed Euler path, again, dealing with arrows here, you still have to have two, but because of the fact that you have two arrows, you're dealing with arrows, you have to have two what I call mismatched vertices. And what I mean by that is, like, for example, look at vertex 1. All right, you have one coming in, two going out. That's a mismatch. All right, Euler path means you have to have two of them. And I'm just looking right here. I mean, looking at 0, you have 0 coming in, 3 going out. That's another mismatch. And then look at 2. You have 2 going in, 0 going out. That's 3 mismatched. The rule is you needed 2 of them. All right, and because of the fact that we had more than 2, I don't even have to keep going, but I just had more than 2. The answer is going to be a big fat no for this one. All right. All right, now we're dealing with a Hamiltonian circuit. Hamiltonian circuit, you're basically connecting the dots, and in this case, you're dealing with arrows, so you got to go with the arrows. You're trying to connect the dots, and because of the fact that it is a circuit, you have to start and end at the same spot. All right. So unfortunately, there's not really a degree rule here. You're just going to have to try to connect the dots. So starting with 0, if I was to start connecting the dots, okay, I just got stuck there. Can't do that. All right. Let's see if I went to 1. If I went to 1, then I wouldn't go over here, and then I get stuck here. So I go ahead and tell you, nothing's going to happen here. So the answer is going to be no, just by process of just trial and error here. All right. Question number 2, Hamiltonian path. Now, Hamiltonian path is where you start and where you end at different spots. All right. Now, here's the thing where some students, they get a little lazy on me. They go like, okay, I'm going to start at 0, and I'm going to just go ahead and start connecting. Oop, messed up there. Let's try that one more time. Let's try this one more time. All right, so they get a little lazy. They go, okay, I'm going to start at 0, and I'm going to do this, and I'm going to stop there. If you notice, this is where I started from. This is where I ended. they're right next to each other, meaning I could just keep going. All right, so that's not necessarily a path, but it's more of an incomplete circuit. So I encourage students to start and end in a way that's not directly connected. So if I wanted to start at, let's just say, start at 1, and if I just started drawing, there you go. Notice where I started, notice where I ended. They are not, there's no way that I can connect these two. So this would be one of many paths that would be correct. All right, for this one right here, a lot of folks having issues with this. Complete means every single graph is touching, or every single dot is touching every other dot. So notice how it's drawn. There, 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 and there. That's all connected. All right, now notice this top dot, we'll just call this A, is touching everything, but everything's got to be touching. Now the question is asking how many edges. So that means how many lines are going to be drawn. So what I'm going to do is I'm going to go ahead and I'm going to just count. So far I'm at 4, 5, 6, 7, 8, 9, 10. So 10 edges. Now, if I was going to ask there's three different ways that this question could be asked. First off, how many edges? It's 10. But it could ask, and that is, how many total degrees are in this graph? Well, let's see. This has a degree of 4. That has a degree of 4. This has a degree of 4. This has a degree of 4. This has a degree of 4. So it would be 20 total degrees. All right. And then the last way it could be asked, and I misspelled degrees, I'm sure. Yep, because I'm going too fast. The last one could be, how many degrees does each vertex have? And so you would say each vertex has 4 degrees. All right. So just be prepared on how it is asked. You might be given several things. Just be sure you're answering the right stuff. All right, next question here. Does the following graph contain a Hamiltonian circuit? All right, so we just already had a question just like this. What you're trying to do is you're trying to connect all the dots and get back to the starting point. Now, but here's the thing. Once you touch a vertex, or in other words, once you touch a dot, you can't touch it again. So like if I start at vertex A, and if I went to B, and if I went to C, and I swing around to D, E, well, if I can't go back to B. All right, I've already touched B. The only one that you can actually touch is the one that you started with. Unfortunately, with this one here, spoiler alert, you cannot create a Hamiltonian circuit with this one. A Hamiltonian path, yes, but not a circuit. All right. All right, next one here. All right, what is the minimum number of colors needed for this map? All right, first off, again, you're going to start. Actually, I could do this real quick. Pause for a second. All right, so using the paint tool is a lot easier. All right, so if you remember with a chromatic number, you cannot have 2 colors touching each other. So look, for example, that's red, that can't be red. That's a no-go. But that can be red because they're not touching. That can be yellow, but nothing else can be yellow because it would be, can't do that. All right, so we'll just do green. Okay, that cannot be green touching, but that can be green. All right. And then lastly, this will be blue. So you do the math, you got a grand total of 4 different colors. All right, for this next one here, it says determine the chromatic number of the following graph. Remember, similar thing with the colors. You just can't have 2 dots that are the same color. So for example, if I wanted to make this red, this could not be red, is directly touching. This cannot be red, directly touching. This cannot be red. This cannot be red. So we got a whole bunch of stuff that cannot be red. So let me clean all my mistakes up. So in reality, nothing else can be red. All right. So let's see if I can do another color here. All right. So if I wanted to make this one a blue, this one can be a blue because it's not directly touching. This will be a green, and this one right here can be a black. So how many colors did I use? I used 4. All right, next one here, Kruskal's algorithm. Now, with the algorithm, what you're doing is you are going to start with the smallest edge and then connect the dots, but not Hamiltonian-like. All right. All right, so starting with the smallest edge, I believe that's a 4. Let me use a different color here to show up. All right, so this right here is what we'll be doing first. All right, after the 4 will be a 5. This right here, there's 2 5s. Now remember, it's not connected at this point in time, but it will be. It's a process. Then here's a 6, and then this 7 will work. Now, you can't do both the 7s, because if you do, you're going to create a cycle. Actually, never mind, scratch that. It didn't create a cycle. My hand was in the way. All right, next one will be an 8. But if you notice, uh-oh, look at that. That creates a cycle. Can't do that. So can't use that 8. If I was to do that, now all of a sudden all of this right here is enclosed. Can't do that. But in reality, everything's connected now, so that's what we're going to do. And then the question's asking how many feet of computer wire. So at this point in time, you're just going to take all these edges that you highlighted or traced and just add it all up. All right, I don't have my calculator with me, so I'm not going to spend the time adding it up in my head. All right, next one. All right, so what is the distance of the longest route? Now, usually there's a tree next to this one, but there's not a tree. So I recommend, and I tell students, go ahead and find all the possible ways that you can go to home, to the bank, to the Kroger, and back to the salon, or to the salon and back home. So I could go home, bank, Kroger, salon, home. So home, bank, Kroger, salon, home. And that would give me, let's see, off the top of my head, it looks like it would be 46. Don't quote me on that. That's 46. All right, next I could go home, Kroger, bank, salon, back home. So when I do that, so home, Kroger, bank, salon, back home. Let's see, I think that would be 46 maybe. Maybe that should have been 48, that first one. I don't know, but you get the idea. All right, then lastly, one more. I know I'm forgetting, at least I know I'm forgetting one. Let's see. All right, so let's say, and I kind of lost my place. I had to pause the video. Let's say home, salon, bank, Kroger. No, I just did that. Home, salon. That okay, that's what it was. Home, salon, Kroger, bank, back home. I think that was it. No, I think, oh, I already did that one. Either way, you get the idea. All right, so again, because of time, I'm going to speed up a little bit. You get the idea. All right, nearest neighbor. All right, so two things are happening here. I'm going to do nearest neighbor, and then I'm going to also figure out how much does it cost when it comes to gas mileage. So my start at home, and the closest place to go is the gym, which is 7 miles away. At the gym now, the bank is closest. But at this point in time, if you notice, I can't go back home because of the fact that I haven't gone to the cafe yet. So by default, I have to go to the cafe, and now I can go home, complete the circuit. So that was home, gym, bank, cafe, back home. And let's see, math on my feet here, 15, 15, grand total of 50 miles. Okay, now this is where students are screwing up, because now you're driving a car that has fuel consumption of 20 miles per gallon. So I'm going to take how many miles I drove, divide it by 20, because that's the MPG, and I'm going to get 2.5 gallons. And then, very simply, I'm going to multiply that by the cost, which is that, and I'm math on my feet here, I believe it's going to be $6.25. I think. Don't quote me on that. All right. All right. For this one here, classify the following. This would be an example of completed. Wow, totally messed up on this one. Connected, sorry. Too many C's. Connected only. Everything's connected one way or form, but the reason it's not connected, or the reason why it's not complete, is just by looking at where a vertex is. If you could draw, like, for example, this vertex, I'm just choosing at random. See how it's not connected to this one here? If I could just draw one edge, one missing edge, then it's not complete. All right, but we've talked about that a lot in class, so we're going to keep going. For this one here, this is going to be a neither. The reason why it's a neither is because notice that the two little, what appears to be baseball diamonds, are not connected to each other. All right. Now, if there was a dot right here, then they would be connected, but unfortunately, there's not. So this is going to be a no-go. All right. And I believe this is our last question, and that is nearest neighbor. Okay. Well, we've already done the nearest neighbor, starting with home. All right. The nearest neighbor is gas. And now, after I've went to the gas station, then the nearest neighbor would be Kroger. And then from Kroger, it'd be the bank. And then from bank, it would be home. So what is the distance? Well, first off, home, gas, Kroger, bank, home. Now, if I was going to add everything, that looks to be 24. Yeah, we're going to go ahead and call this 24 miles. All right. That's everything. That is part 4. Hope you enjoyed it. So, yeah. So, good luck on your final. Have a good day.